All right, so we have a manometer. Looks like this. This is open to the atmosphere. And we're trying to figure out what P1 is. So this is atmospheric pressure, so we look that up or measure that separately. And then looks like this. And the height here, the height difference is 0.25 meters. And we've got water in here. So which pressure is bigger? The atmosphere, so P1 is going to be less. So we'll write the manometer equation. All right, so let's see, we need the atmospheric pressure. We looked that up in the standard atmosphere. So we got that. We're going to stick that in here. We're going to solve for P1. Anybody know the density of water? It's what? One what? Yeah, so actually that's how a gram is defined, right? So it's 1 gram per cubic centimeter. But we need this in terms of kilograms because newtons has kilograms in it. So we have to multiply by 100 centimeters per meter. And we need 3 of those. Cancel out the centimeters to the third down here. And then we need 10 to the third grams per kilogram. We just need 1 of those. All right, so this cancels out the grams, this cancels out the centimeters to the third, and then we're going to get kilograms per meter to the third. So it turns out this is 1,000. So that's what we need to put up there. Gravity is 32.2, right? What's wrong with that? That's English. So again, if we're watching TV trying to do our homework, we need 9.81. And then H is 0.25 meters, so we stick all those numbers in, and that's going to solve to give P1. So you guys do that. Pull out your calculator, plug in the numbers, and crunch away for me. So what'd you get? Shout it out. 9, 8, 8, 7, 2. So 98,000. What are the units? It's got to be newtons per meter squared. So make sure you work the units out. That's pretty standard stuff now. No, we ought to be able to get that. So that's how you can use water in a tube to measure pressure. And in fact, you'll do this in the lab when you take the lab course. Is we'll have, sorry, that's an airfoil. We'll have a flat plate. Now that's not in this class, that's in the experimental methods class. You'll have a flat plate, and as the air flows over a flat plate, the velocity closest to the surface is lower because it starts hitting the bumps in the surface. It's called a boundary layer. So the velocity here gets real low, so what we'll do in the lab is you put a little tube connected to a hose, and then it goes to a manometer bank, and you put water in here. And you can measure the pressure in the flow at that point with that tube. And in fact, you put multiple tubes. It's called a boundary layer rake. So you put a thing that has a whole bunch of tubes so that you can measure how the flow increases or decreases with height above the plate. Okay, standard atmosphere. Is defined, because that's what they can measure, is defined as temperature as a function of altitude h. Because you put a thermometer on a balloon and you send it up and it records the temperature as it goes up, then the balloon bursts and comes back down. And you can get this. And then from temperature, and then the hydrostatic equation, that's the equation we did last time that tells how dP is related to dH. Then you can get pressure from that related to altitude. So here's temperature versus altitude, there's pressure versus altitude. And then we can use the equation of state, the ideal gas equation, to get the density. And so that's how the tables in the back of the book are calculated. So it all starts with this thing here, and the graph that's the definition of the standard atmosphere is in your book. So this is on page, in 8th edition, page 117. And I'm going to put it up on the screen here. All right, so this is the chart or the graph that's in your book. And temperature's on the bottom. So this is a little bit opposite, right? We're talking about temperature versus altitude. Temperature's on the bottom, and altitude, because it's going up, is on the left side. So it seems natural to do that. And at sea level, the temperature is defined as 288.16 degrees K. And then in a region of the atmosphere called the troposphere, right here, and these labels are not in your book, so I encourage you to write these names in your book. So on this figure in your book, maybe in pencil so you can erase it if you want to sell your book, although I would keep this book. It's got a lot of arrow stuff in it. So during this region, the temperature goes down from sea level upward till about 11 kilometers. And then this temperature stays constant in what's called the tropopause. And then the temperature increases in the stratosphere. And then it stays constant in the stratopause. And then in the mesosphere, it goes back down. And there's more to it. If you scroll up, there's the thermosphere as well. I'll scroll down. So right, troposphere, tropopause, stratosphere, stratopause on this graph. And these are the layers of the atmosphere. And this temperature graph determines what we consider the standard conditions at any altitude. So in this graph, there's two different regions. There's what's called the gradient region, where the temperature is changing. And then the slope, notice it tells what the slope, how fast per kilometer the temperature is decreasing. And then there's what are called the isothermal regions. Okay, can I move past this? Is anybody still writing the names down? All right, just for the heck of it, and because when my kids were young, this is another document. I'll remember to upload this to Blackboard so you can read it. Another document describing the different layers. I need to rotate this. Any of you guys watched the movie when you were kids called Finding Nemo? You remember Mr. Ray? He'd sing the song about the layers of the deep blue sea. So I thought just for the heck of it, I'd remind you what those are, because there's layers of the atmosphere, right? There's epipelagic, mesopelagic, bathopelagic, and abyssopelagic. So just like the atmosphere, we have names for the different layers. In the ocean, Mr. Ray sings the song about the different layers in the deep blue sea. You guys remember the song? Am I missing any? I think that's what he sings, right? I think I tried to look for a clip of that on YouTube, and I don't believe I found it. I'll see if I can find it again. In the atmosphere, we can survive as humans, even though the oxygen goes away. You can be on the top of Mount Everest at 30,000 feet, and if you've acclimated to the air, you can survive there for a while. Whereas if you go all the way to the bottom of the ocean, the pressure is so high that it's tough to survive there as a human. And even if you go down 60 feet in the ocean scuba diving, the pressure gets high enough that it traps gas in your blood, and then if you come up too quickly, the gas comes out of your blood in bubbles, and you get the bends and could potentially be crippled or die. So the atmosphere is much more friendly to us than the ocean, although I love swimming in the ocean and snorkeling. All right, so that's the layers of the atmosphere and the layers of the deep blue sea. So I'll quickly write up there what I was saying earlier is that there's regions that are called the gradient region and then the isothermal regions. So the gradient region, like the troposphere, the formula for the temperature is that slope times the altitude, and then this is just that starting temperature at sea level when H is 0. And then in the isothermal, like in the tropopause, the temperature is just constant at that value. So then you can see that from the chart. All right, we did that, we did that. We did the layers of the sea. Okay, so you're watching the weather, or you're looking at the online weather forecast. Maybe every once in a while you watch the Channel 12 weather forecast. And the weather forecast, the meteorologist will say, it's a really hot day, and the dew point is really high, so there's a good chance of severe weather. You've heard that, right? Why is that? It's related to how the temperature changes in the atmosphere as air rises. So we're going to talk about that. Why clouds form. It's because of this gradient region in the troposphere. By the way, this is not in your textbook, but it's still important. So clouds form when air rises. Because the temperature goes down and then the water vapor in the air starts to condense out. So the air can rise due to ground heating, or if the air is going up a mountainside, the air cools as it goes up there and clouds form. Or you could have upper level high and low pressures. So you get a high pressure region here and a low pressure region here. Air will flow into the low pressure region and it will rise. So here's a picture of what's going on that hot summer day when the dew point is high. So this is the ground. Down here the temperature is 105 degrees F. That's hot, right? So this is 13.6 degrees K. And the dew point, there's a lot of moisture. The dew point is 75 degrees F, which is 296.9 degrees K. And the dew point is determined by if the air with the moisture in it right now cools down to that temperature, then water vapor starts to condense out. You can actually measure the dew point. You take a glass of water, glass is best, put water in it, put a thermometer in it. It's at room temperature. And then you throw ice in it, and then you record the temperature at which the water starts to condense on the outside of the glass. And that's kind of close to the dew point of the air in the room. Okay, so we have this, would be called a high dew point and a high temperature. And the air is hot, so it starts rising. And the temperature is going down because the air is expanding as it goes up in the atmosphere. Molecules get farther apart because there's less weight of the air above on the molecules pushing them in. So they get farther apart. Pressure goes down, temperature goes down, density goes down. Eventually, the temperature up here equals that dew point, and you get the clouds start to form. So this is the cloud base right there. So we can calculate what that altitude is. By taking the formula for how temperature varies and setting the temperature equal to the dew point, and then what altitude that temperature is hit is the base of the cloud. So here's the formula for how the temperature varies. And the temperature of the ground is 313 point. I wrote slide 313.6. I don't know what, oh, this is my arrow. That's what's going on. There you go. Well, this doesn't look like the formula I just wrote up where this was 200 and, what was it, 288? That's because that formula was standard atmosphere. This is not a standard day. It's way hotter than standard atmosphere at sea level. But the slope here is still valid. That's how the atmosphere behaves. And so this is for this high temperature atmospheric condition. This is not standard atmosphere. And then we're going to set the dew point is 296. And so we can calculate the H, that's the cloud base. Everybody follow what's going on? We're saying the atmosphere behaves with the temperature going down at that slope. We're at this temperature on the ground, so it goes down that fast, and eventually, as we go up, it will hit that temperature. And so the cloud is at 2569.2 meters, which we convert that to 822 feet. So the cloud will be forming at 8,000 feet. Is that low or high? The top of the troposphere, so we're saying that this cloud base is about 8,000 feet. The top of the troposphere is like 36,000 feet. That's where the temperature stops decreasing. So the cloud starts to form, the air still keeps rising and condensing out, and so you get this huge giant cloud building all the way from 8,000 feet up to 36,000 feet. A lot of room for that big thunderhead to form, and that's why you get a big thunderhead, is there's all that space above where the cloud starts to form the cloud. You know that anvil shape on the thunderhead cloud that you'll see sometimes? Cloud will look like this. You get this flat top, and then the wind actually blows like that. This is the top of the troposphere. The temperature stops decreasing, so there is no more condensation, and the cloud is done. All right, let's say we had another day. And on this day, we still have the same temperature here, but let's say the dew point is low. You got to cool the air down quite a bit, all the way to 40 degrees. So it's really dry air near the surface of the Earth. And so if you use that number in for the dew point converted to degrees K, let's write that up here. So if the dew point is 40 degrees F, then the cloud base is 19,991 feet. The cloud does not form until much higher in the atmosphere, has less room to develop before it hits the tropopause, the top of the troposphere, and so you don't get a big cloud, the big thunderhead in the severe weather. Now, if you really want to study this more, you can take a class in meteorology that studies this, because this is an approximation. Actually, the dew point changes slightly as you go up in the atmosphere as well. But I'm not including that. That just confuses everything. And we're not trying to accurately predict the weather. We're trying to understand the atmosphere. Okay, questions about that? How are we doing on time? All right. So the key feature of this is that when we talk about temperature, density, and pressure at certain altitudes, we're usually talking standard atmosphere. But we can always adjust things if we need to be a specific temperature or density. But if you're working a homework problem or you're calculating performance of an airplane and you say an airplane's flying at 15,000 feet, you go to the standard atmosphere, you get the information from that, and that's what you use for the density, temperature, and pressure. All right, so the standard atmosphere is T as a function of H. And we get that from the formulas, which are on, actually it's the graph. And there's formulas on the graph, right? It's either constant or it's sloping. So if we want to calculate pressure, we've got to use this thing. And that's good. It's got temperature in here, so we take the readings from the graph and we can put them in for the temperature. And let's say we want to calculate this, but we still don't know this, right? So we got 3 variables here and only one of them's known, so we need another equation. And what we have is the hydrostatic equation that tells us how pressure varies with altitude. So we can combine these 2 equations. In fact, we can eliminate this unknown here. So rho is going to be P over RT, keep our minus sign, like this, and we know the temperature variation is a function of altitude. And so now we have an equation where we know this thing, and we can solve for P. Unfortunately, it's a differential equation, but we can solve that. In fact, this is an easy differential equation. You can just integrate both sides of this. So we want to get all the P's on one side and all the H's on the other side so we can integrate. So and this side has all the P's and this side just has DH, and temperature is a function of altitude. So all of the H dependencies on this side, all the P's on this side. So let's say we're in an isothermal region. That means T is constant. Notice I picked an easy one here. So if we want to integrate from one altitude 1 to a different altitude 2, that's what we do. Notice I can pull the temperature outside the integral because the temperature is constant. So I can pull outside. And remember, integration is not magic, right? You've done this forever. We're just adding up all of these changes. So we're saying, well, we start at altitude H1, and we add up all the DHs until we get to H2. And on this side, as we do that, we start out at P1, and then we keep adding on to that P1 the extra dP over P's until we get up to the next altitude. And this one we can carry out exactly. We can get a formula. So we know what the integral of 1 over p is. That's something you've learned in math, right? So 1 over p becomes the ln of p. And we evaluate between the limits here. And the right side is easy. Temperature is constant. dH just turns into H2 minus H1. So what this says is if we go up in altitude this much, then we plug in these limits. If we go up in altitude that much, then we change in pressure this much. And in fact, we can connect this together, right? The property of the log is that a difference turns into a product. And then we can get rid of the log by taking the exponential of both sides, because the exponential is the anti-log. And so you get a formula of P2 over P1, and this tells you how it changes with altitude. Do we do this in our homework problems and when we're calculating things? No. But this is where the tables in the back of the book come from, these exact formulas. So you can calculate, and if you wanted to write a program that calculated standard atmosphere for you for some reason, you're doing that for part of your job, you would use the formulas like this that are in the book. If you're going to work a homework problem and you have the atmospheric tables, you use the tables. So this is the go-to method for most calculations, is the tables in the back of the book. That's Appendix A and B. Now, this is an isothermal region where the temperature is constant. If you go to that region where the temperature is a gradient, slope times temperature, then it gets a little more complicated, but you can still do the integration. They do this in the book if you want to read through how they do it. But again, I'm not going to spend a lot more time on it because we usually use the appendix and the tables for what we're doing. And with the tables, you can answer this question. You're in a balloon. You know that you need an oxygen mask if you're about 20,000 feet, and you read the temperature on a thermometer, it reads 429.5 degrees R. Do you need oxygen? You don't know until you look up that temperature in the tables, and we'll do that next time. Of course, I guess you would probably feel the fact that you probably need oxygen when you're at that point anyway. So that's where we'll start next time. Again, make sure you get your homework uploaded on time on Blackboard. I'll see you on Friday.
What do you say the mass for temperature was?